Good afternoon, I am Mr. Thank you for joining me for this video. We're looking here at limits in two variables. Up till now we've always looked at single variable limits because we were doing single variable calculus. When you're doing multivariate calculus, then you'll see limits involving two. These are your multivariable limits. What is your basic essence or format? It's this: limit as a certain function which is represented in terms of two variables is approaching two values a comma b. You have a certain function in terms of those two, or an expression, equation. What is the end result? When you're doing these type of limits, it's not as hard as one would think. You're always keeping these two items in the back of your head. Is there continuity involved? Is there lack of ambiguity involved? Where? At that point of evaluation. These are the functions which are expressed in the form z is equal to x comma y, where you have a certain expression in terms of x and y, and your third variable would be the z. You're looking here at items which are always then in the z-axis, then here's your x-axis, then you know your y-axis over here. You would have representations which would involve z, x, and y, and that's where this comes into play. When you're looking at this x and y approaching a specific value, is at that particular value continuity seen? If there is there a lack of ambiguity seen, meaning it's clearly defined? If there is, then you'll have an outcome over here which will be good. These questions can be very easy, these questions can be quite tricky. In this video we're focusing on the essence of these type of limits. I'll show you just a few examples. We'll close it out with a good example, but we're not doing everything here from A to Z, we're starting it out. Let's look over here at something easy. Limit as x approaches 1, y approaches 1. We have the equation x plus y. What would your equation be here? Really, it would be z is equal to x plus y. You can graph this out on the three-dimensional graphing tool. I can show you some of this shortly in this video towards the end. What would be the outcome of this particular two-variable limit? Your best technique always is substitution. If you are putting in a value of x and a value of y, and you're getting a value which is clearly defined, you know it's working, there's continuity involved, there's lack of ambiguity involved, and it will be correct. You'll just do 1 plus 1 and your end result here will be 2, and it will be correct. What does it tell you? At this particular point for this system, z is equal to x plus y, there's continuity and there's lack of ambiguity, meaning you have a clearly defined point in terms of z. You'll see that, and when I show it to you, we can graph it out, you'll see it on our online tool. But this limit is solved, it's good. Look over here, limit as xy approaches 0. 0x, 0y, x equals 0, x equals y. You have x squared plus y squared minus 3 equals what? What's the outcome? You're always thinking about substitution technique. Plug these in. If you have a clearly defined answer, it will work out. If you were to graph this out, you would have a paraboloid, and you would see it would be equal to this representation, z is equal to x squared plus y squared minus 3. We can show this to you when we graph it out, and you will see something. There's a vertical translation down. You put 0 in place of x, you have a 0 plus 0 minus 3. Your end result here is a minus 3, and it will be correct. And we can show it to you graphically. At this particular point right here, 0 comma 0, for x and y, you have an output which is good because there's continuity over there and there's lack of ambiguity over there. That limit outcome will be good. Look over here, limit x comma y approaches 2 comma 2. We have that x plus y divided by root of x plus y. Your other technique other than substitution is always to simplify to the greatest extent what you can. I can simplify this. I have x plus y to the power of 1 divided by this. You're looking here at a simplification such that when you simplify this with that exponent, because this is what you have, x plus y to the power of 1 divided by x plus y to the power of 1 over 2, when you bring this up, you will end up seeing just in the numerator x plus y. This right here is equal to just root x plus y. This here is indeed the function which is coming into play. Z is equal to square root of x plus y. Now you can put 2 in place of x, 2 in place of y. You will have this square root of 2 plus 2, which will be root of 4, and your end result here will be 2, and it will be good. At this particular point for this limit, for this system, you have continuity, and which is why we're getting a good answer. So you're seeing how the questions play about. For the purposes of this video, I won't show you any more such examples, but I will show you one more question which will be slightly more tricky, and we'll solve it out and we'll close out this video. Look here at this question, limit x comma y approaches 0 comma 0. I have that xy divided by x squared plus y squared. This here is our equation or our system which is being solved, which would be z is equal to a certain function in terms of x comma y. As always, you're thinking about continuity and if there's clarity or lack of ambiguity. Now you're thinking about that, and the best way to think about it is to plug in what you have. When I plug in x equals 0, y equals 0, I have a 0 times 0 divided by 0 square plus 0 square, and I have an indeterminate form which pops up. That shows ambiguity, and it shows that possible continuity is not present at this particular point for this system. And I'll graph this out for you later on, and we'll see what it looks like. Anyhow, what do you do over here? You don't necessarily have to start thinking about derivatives and all of that. You can think about a method of approaches, and what do I mean by that? And I'll talk about it. It's a good, reliable technique to use different approaches or use different paths. These are different terms for the same technique we're talking about. Use different paths or different approaches. What are we referring to? Think about this equation right here, or function f of x is equal to x plus 1. When you graph it out, you know if x is equal to 0, y is equal to 1. When y is equal to 0, you have this. This is what it looks like. What is the domain of this system? You know it's minus infinity to infinity. When you are looking at approaches and paths for single variable limits, because you would have a limit as x approaches 0, you'd have this function x plus 1, and you know you're solving out. It's easy. When you're looking at single variable limits, you're looking at an approach and a path. You're always doing left to right. I'm looking from left to right across this entire domain, minus infinity to infinity. This function is entirely continuous. There's no discontinuity in it at all. When you're doing your single variable limits, you're looking at a single approach, a single path. Your single path is always left to right with regards to the domain. Is there continuity or discontinuity present? And you see that to be the case frequently when you're looking at rational function limits. If you were looking at this 1 over x plus 1, and then you change this to, let's say, a minus 1. Now all of a sudden things have changed. I've changed that limit because now I'm looking at a rational function. What's the domain of this function right here? Your domain would be x is an element of all real numbers, except x cannot be equal to what? X cannot be equal to minus 1. And that right there is a discontinuity. If you were to graph this out, what are you looking at? You have a horizontal asymptote, which is your x-axis, y equals 0, but you have a vertical asymptote, which is right here, x equals minus 1, and that's exactly where you're evaluating your limit. If you were to graph this out, how would it look like? If x were equal to 0, then you have a 1 over 1. You have here a graph which is coming out like this. You know when you start looking at the domain from minus infinity, and then you have a discontinuity at minus 1, then you jump from minus 1 up to infinity. When you start looking at from left to right, because for single variable limits you're always judging from left to right. I'm looking good and it looks good, except here I have a discontinuity, then I continue onwards. You're always using a single path and approach. Why am I stressing this out so much? When you're doing multiple variable limits, this concept from left to right doesn't apply anymore fully or at all, because now you have to start thinking about multiple approaches, and let's talk about that. Multiple paths. So you have to start thinking about multiple paths. Here I'm thinking about only a left to right path, but what are my different paths I will think about when I know I have an ambiguity after I'm plugging in these values, because I'm getting a 0 or 0. I can think about different paths. One would be x equals 0, one can be y equals 0, one can be x equals y, one can be x is equal to minus y, or you can say y equals x, or you can say y equals minus x. You can even throw y equals mx plus b, different paths, because now you're looking at different approaches, and if the result from each of these approaches is the same, you will have a limit which is good. If you're getting different results from these different paths, then you have a limit which is undefined, meaning a limit does not exist. How do we utilize these paths or approaches? If I'm saying x is 0, then wherever I have x here, I'll put a 0. Let's look over here. X is equal to 0. I start putting in zeros. I have a 0 times y over 0 plus y square. I'm looking here at a 0 over y square, and I'm getting here 0. When x is 0, my limit output is a 0. We'll keep that aside over there. What about when y is equal to 0? You can start plugging in y equals 0. I'll have x times 0 divided by x square plus 0 square. When I do this, I'll have here a 0 over x square, and I'm getting a 0. In these two approaches, I'm getting same outputs, which is looking good. But what about when I do x is equal to y or y equals x? When I do y equals x, x equals y, I'll put y in place of x. In that case, I have a y times y divided by y square plus y square. What do I have? I have a y square over 2y square. When I simplify it, I have here a 1 over 2. That's my one output. How about if I were to think about this, x equals minus y or y equals minus x? In that particular case, I can put a minus y in place of x. When I do that, I have a minus y times y divided by minus y square, which is just a y square plus a y square. Here I have a minus y square over 2y square, and I'm getting here a minus 1 over 2. I've tried 4 different paths, 1, 2, 3, 4, and I have 3 different results. I have 0, 0, I have a half, a minus half. I have 3 different results using 4 different paths, but there's no consistency here with regards to the results. My results are different based on different approaches, different paths. Hence, for this particular limit, we will say that the limit diverges or the limit does not exist. You can say either it diverges, and there's nothing wrong with saying that, or your limit does not exist. Either of those answers will be correct. Now that we've solved this out, we've come up here with D and E does not exist and diverges, that the limit does not really exist. We've seen here the play of the approaches and the paths. Let's shift over to the computer and we can look at graphically what all of this means and some of the previous examples. Let's look at 3 of the graphs for the limits I presented. We're not going to do them all, but we'll do at least 3 of those. And this is Desmos 3-dimensional graphing online website. Right here in this top box, I'll put a function equation x plus y, because we're looking here at z is equal to x plus y. I'll write it out, x plus y. When I create the image, this is what we have. A plane on an x and y and z axis. I've demonstrated an x plus y, it's a plane. When you're doing limit as x approaches 1 and y approaches 1 or whatever finite value, you are looking here at an output which is clearly defined. You're doing 1 plus 1, which is 2, and you look right here, x is equal to 1, y is equal to 1. You look upwards at a z value of 2, you have continuity right over here. As you would see, there's a continuity and there's a lack of ambiguity. It's clearly defined. X plus y is 1 plus 1, which is equal to 2. The limit as x approaches 1, y approaches 1, we have an output equal to 2, and it's good. Continuity and a clear definite answer is present over here for that limit. Let's change the limit to something else. We'll come back over here to this box. The other limit we can show you was the one which was a paraboloid, x square, and then we'll do plus y square, and then we can do minus 3. And this was the limit where we did limit as x approaches 0 and y approaches 0. This equation, x squared plus y squared minus 3, where does it approach? It's a paraboloid. This is what it is. There is a vertical translation down by 3 units right here as you're looking at the base. This right here represents x equals 0, y equals 0. Your output is clearly minus 3, because you can put literally 0 in place of x, 0 in place of y. You solve it out, your end result is a minus 3. A paraboloid translated down by 3 units. That's exactly what the output is. There's continuity over here, and there is here a clear definite answer, minus 3. But you can see how the interaction is of the x and the y and the z axis. The output of these limits are going to represent your z value. Let's look here at the last example I presented here in the video. It was limit as x and y approach 0. We had xy divided by x squared plus y squared. Let's graph it out. We have xy in the numerator, and then in the denominator we had x squared plus y squared. Let's bring in the camera into the view. xy divided by x squared plus y squared, z is equal to all of this. How can we verbalize what this graph looks like? It's not easy to verbalize it, but this is what you're looking at. X-axis, z-axis, and then we have a y-axis. I'm looking here at the original equation. Now I'm coming here from underneath it, and let's start zooming in. When I'm going to zoom in over here, this is what I'm doing here. Your graph is essentially faded out. It's all faded out because we're so zoomed in. The graph is outside of the boundaries of what you see, the grid over here. We have a discontinuity here around the origin. As I start zooming back in, the graph will come into play, and we are seeing a graph as it originally was. But you can see there's an apex over here, triangular apex. That apex represents the discontinuity where the limit is being evaluated. And here's the origin right over here. The discontinuity totally encompasses the origin. Hence, the limit did not exist because there is no graph present over there. There is no representation of this equation or system or function at all around the origin. It's entirely discontinuous. The limit will not exist. So we will close out the video with this graph over here, and you can see z equals equations have an x and a y variable. When you evaluate their limits, then you have multivariable limits come into play. Thank you for watching.